What I'm supposed to talk about this time is radiometric quantities and their measurement. If you look, okay, so this class is satellite. What is the name of the class anyway? I can't even remember what the name of the class is, but it has something to do with satellite validation. And what we focused in so far is up this inherent optical properties, which didn't work out too well here. But anyway, we've been working up here, but really what the satellite measures isn't any of that. What the satellite measures is light coming from the water. And so what the satellite is measuring is some, radiance at the top of the atmosphere. And so it's radiometric things. And so what we're going to talk about today, and we're going to do the lab, I guess, tomorrow, of radiometric measurements, and it's all to prepare you for measuring the light field in the water. And then when we go out on the ship, on the boat, whatever you want to call a boat that large, when we go out on Monday and Tuesday, whichever group you're in, we'll be making a combination of the IOP measurements and the radiometric measurements. I wish we had gotten to go out yesterday. I wish that was the field day, because it was absolutely gorgeous out. I went out around White Islands, you'll see where those are, and it was like no swell at all, but about 10 knots, just gorgeous day. Anyway, but what we're going to do here is we're going to play around and learn about these different radiometric parameters. So while radiance, as you saw in this chart, although I didn't point it out, radiance is like, the radiance distribution is like this central thing. It's easier to describe things when I talk about instruments and stuff, starting with an IRradiance detector. So when we start talking about the instruments here, I'm going to start with IRradiance, and then build my description up to radiance. So what I'm going to do basically is talk about spectral resolution of the detectors. We'll do plane IRradiance, scalar IRradiance, and the radiance and radiance distribution. So that's what I'm trying to get through here. And then everybody, the instructors all wanted to add a little bit of extra things at the end. So at the end, there's going to be a few extra little factors thrown in. But this is basically what we're going to try to do here. To remind you what we're trying to measure, this is what we're trying to look at. This is the downwelling IRradiance. It's got, if you look from the visible, this is a visible from 350 probably up to 950 nanometers. There's all these nice sharp spectral lines that I described using the other day. But it's got basically a broadband black body radiation curve modified by these spectral bands and modified by atmospheric absorption bands in different spots. So that's what the downwelling surface looks like. And we had this upwelling surface that's peaked in this is clear water, so it's peaked in the blue. And that's what we're going to be trying to measure, is different features in that light field. I'm going to start, instead of going right into detectors, what I'm going to start is describing the three classes of spectral characterizations of the detectors, because each of these detectors, once I have those down, each of the kinds of detectors, you can get one of any of those that you want. And when we talk about the spectral, the wavelength of a filter or the wavelength of a measurement, the terms we use are the full width at half maximum. And the full width of half maximum is you take the peak and you find where 50% of that peak is, and you find the wavelength there and the wavelength there, and the full width of half maximum is the width of the difference between this wavelength and that wavelength. Okay, so that tells you how broad the filter is. And then when you try to choose what wavelength that filter represents, we don't use the peak, because in general, these things are really screwy looking for interference filters or whatever. They're not just this nice Gaussian or a nice square peak. They have these weird structures in them. And so by picking a peak, you can get a sort of a bad number for what the wavelength is. And so what we define the filter by is by the band center. And so the band center is basically halfway between the maximum, the larger full width to half, well, the larger half maximum and the smaller half maximum wavelength. Okay, so that's how you define this, the filter center, not by picking up the peak. And so here's a couple typical filters, somewhat typical. I'm trying to remember where I got these from. It's not that important, but anyway. So this has a full width to half maximum, pretty wide, about 40 nanometers. This one's about 74 nanometers, and you see how that's defined. So that's how we define the width in the center of the bands.
I1, I2.
Okay. Well, now you just told me where I got these from. Where do you see I1 and I2? Up at the top.
Below band center.
Oh, now yeah. So you told me where I got these from. These are VIIR's passbands for satellite instrument. So these is band I1 and band I2 from the VIIR's instrument. Okay. Irrelevant sort of for what these are just two examples of filters. All right. And in fact, I believe I probably just screwed up because I think these are probably these graphs are probably ITAR restricted of some sort. So if you're not from the US, forget you ever saw this graph, please. Okay, but you can get the full width to half maximum. So there, okay, so we have two, maybe three classes of detectors that I'm going to describe based on their spectral resolution. The first we're going to go through is PAR or some other broadband, so things that have bands that are very, very wide. Maybe you're only measuring one spectral band at a time. PAR is an example. There's sensors that measure UVA. In the old days, we measured photopic, which was based on the eye response, centered at 550 nanometers and very, very broad. In fact, almost all of the instruments in the 50s and 60s were basically one filter in this photopic to try to match the eye response. You had to do something one wavelength, so choose that. The next level in information is multi-channel instruments, multispectral instruments. They're a collection of individual bands, say 10 bands. It depends on how many you want to put in there. In ocean optics, they were typically 10 nanometers wide. Okay, so the full width at half maximum was 10 nanometers. And so once the electronics got good enough that we could go beyond single channel, we went to multi-channel, and there's still a lot of instruments around there, and they still, like the AC9 or for IOPs, but for radiometry, they still do a really good job because most spectral features are pretty broad in the ocean. And then the next level is, people have asked me about this a little bit, is hyperspectral. And hyperspectral means that we have measurements throughout the visible spectrum, every few nanometers to every 10 nanometers. But the main idea is you have a continuous spectrum of measurements placed all the way through the spectrum. So it's, in terms of information, you go from PAR to multi-channel to hyperspectral. And nowadays, pretty much everybody buys hyperspectral. I know, and I'll explain that when I get to that part. But each of those, when you have eventually when you have a hyperspectral instrument, we'll use gratings or prisms or something to disperse the light. And then you have a whole bunch of detectors behind there. So eventually you have detectors spread through the wavelengths. And these detectors will have a spectral bandpass that they're detecting that you should describe in terms of its full width at half maximum and such. There are groups, though, that do try to do something like a hyperspectral sensor with a whole bunch of individual sensors, so it isn't necessarily exclusive. Diffraction grating, yeah. Well, there's all sorts of different kinds, but diffraction grating, yeah. Okay? Okay. So we'll start with a simple one for spectral, PAR. You've already heard about this, photosynthetically available from 400 to 700 nanometers, equal weight to each photon. A silicon detector, if it worked perfectly, would give you a measurement that's just dependent on the number of photons, because each photon would come in, create a photoelectron. If you remember Einstein and the photoelectric effect, you generate a photoelectron, and that's actually what you measure with your electronics. It's this photoelectron. Unfortunately, a silicon detector absorbs blue light that doesn't necessarily create the photoelectron. You can get a reabsorption of the photoelectrons. There's reflections from the surface of the detector. There's all these other issues that come in, so that a silicon detector is not exactly a good quantum detector. So there's other issues that make it harder to measure PAR than it should be with a detector. And so in the end, it's a simple measurement to describe. You're trying to calculate the number of electrons, but it's physically not that easy to build a really good PAR detector. Okay, so there's going to be approximations going in there. The other thing with this broadband, another broadband, as I said, is photopic. The thing about these broadband instruments is they're really hard to calibrate accurately, because if your light source that you were calibrating with looked exactly like the light source that you were measuring the light field with, or that you were measuring in the world, everything would be good. But with spectral differences between the two, if your detector isn't perfect at getting the quantity you want, like if a PAR sensor isn't perfect at converting every photon between 400 and 700 to a photoelectron and measuring that, then you're going to get a calibration number that's going to depend somewhat on the spectrum of the light you're looking at. And let me go back for a second. Where did I go? There. If you look at the upwelling light field and you look at the downwelling light field, and you think about a calibration lamp that you use in the lab, unfortunately is not as hot as the sun is, or maybe fortunately is not as hot as the sun is. So the black body curve for a lamp is probably peaks somewhere up in here. So it has very little blue light, and it's going up tremendously in the infrared. And so when you have a calibration source that looks like that, and you try to measure this or you try to measure that, you're going to get different answers. So calibrating a broadband instrument is a really difficult problem. Okay. Next thing, multi-channel. Typically 10 nanometers wide, as I said. Use 10 nanometers because most ocean parameters don't have really sharp features. Satellites, because they have to get signal to noise down low enough, have fairly broad channels, like I showed you the one for I1 and I2 there for VIIRS. CWIS bands were 30 nanometers or something on that order. There was, for a while, one company was trying to match exactly the CWIF bands with their radiometers. And so that might be one reason to use a multi-channel instrument. If you look at reflectance, all those sharp atmospheric features cancel out somewhat because they're in both the downwelling and the upwelling, and reflectance is the ratio of the two, so they'll cancel out. So we use these 10 nanometer filters, some sort of approximation. The spectral channels are defined by filters, typically interference filters. They have some spectral shape defined by band center and width. And when you're using one of these instruments, you have to be careful about basically out-of-band effects. When you're looking at different colored sources, the world versus your calibration source. And I didn't point it out before, but this is the light that you typically want in the filter. And they all are going to have some sort of out-of-band response that you have to be careful of. When you buy a commercial radiometer to use in the ocean, what you want to try to do is get these things to be less than 10 to the minus 4 of the peak values. What's that? When you try to do the an interference filter is made up of laying dielectrics down and trying to get the interference such that you only get the wavelengths you want and not the other ones. When you build a filter to do a nice sharp response here, you end up sometimes with things out there. And so what you have to add, what the manufacturer adds, are colored glass filters a lot of times to try to knock these things down. But now, this, I don't want to focus too much on the exact things here, but this is a satellite instrument that someone spent millions of dollars building, and probably millions of dollars building these filters, and even they have these out-of-band effects left in there.
That's huge. That's 20%. You're saying 10 to the minus 4.
It's not 20. Yeah, no, that is huge. The peak is huge, right? The proportion of this in total area is relatively small, but what's that?
It's not 10 to the minus 4.
It's not 10 to the minus 4, no, but yeah.
So how would you distinguish those out of bands if you are looking at a full spectrum and not just like a single?
Okay, so what you have to do is characterize your system by throwing in monochromatic light throughout the visible spectrum. Okay, for these, and that's how you characterize the these multi-band.
Jeremy Wardell, when he talks about atmospheric correction, they do an out-of-band correction for whatever instrument it is, because if it's the Beers sensor at 6 whatever here, they've measured that out-of-band response, and then they have a little fudge factor that they put on that top of the atmosphere measurement to subtract out 10% or whatever this was out of band.
Okay. So that's just a separate step.
So part of the atmospheric correction process, yeah.
But you can imagine that if you had that sensor and it was an in-water sensor, right, where you have virtually no light at 800 nanometers and a ton of light at 400, when you take that spectrum and you multiply it by the light spectrum that's available, all your signals are going to be from your out of band. So you hadn't characterized it.
So if you remember the inelastic lecture I gave the other day, when I said that when people were getting these new instruments that were multi-channel, and we started seeing these weird diffuse attenuation coefficients less than the absorption of water, one of the things we looked at was to see if our radiometers were screwed up and had this out-of-band response. Or so as Colin says. Okay. Hyperspectral. Continuous spectrum, really it's channels every 1 to 10 nanometers. Typically you have a grating or a prism for dispersive elements. So you have light coming in, you have some sort of a slit that defines the geometry of the light coming into the detector, a dispersive element of some sort, and it spreads the light off as a function of wavelength into different places, and then you have different pixels picking up the different detectors picking up the different light wavelengths. The nice thing with a hyperspectral is you can build integrated channels. You can average a bunch of channels together and exactly match different satellite sensor channels in terms of if we're worried about satellite validation. You can pick up different absorption bands for phytoplankton pigments and such when you're working with like that. So hyperspectral, everybody's going hyperspectral pretty much now. You have to be careful of several things when you're using a hyperspectral detector. One thing I'll show you a picture in a second is like we have out-of-band effects in multi-channel instruments, hyperspectral instruments always have some sort of a scattered light effects. Okay, so we call it stray light in the system that will take light that is from a different wavelength and throw it onto some other pixel and mix things around so your measurement isn't quite what you think it is. Resolution limits. Now, it's important when you buy a hyperspectral instrument, understand that there may be, you could put a zillion detectors here and get a detector every nanometer if you like, but that isn't really the spectral resolution of the instrument. The spectral resolution of the instrument is, at this detector, what's the full width to half maximum of the signal that it sees, okay? So those are two different things. One example is we're going to be playing with HyperPro instruments. Here's an example of a HyperPro irradiance detector. They have channels every 2 or 3 nanometers, which is cool, but the bandwidths are on the order of 10 nanometers. So it doesn't, there's a limit to the spectral resolution of each of the sensor. And that spectral resolution is a function of the slit width. It's a function of the dispersive element that you're using there and the size of your detectors. The stray light that I'm talking about, here's a nice picture Stephanie from the Moby project set up. If you look at an incident ray and you have a reflective diffraction grating, incident ray comes off, it'll come, you would like, say, the wavelength that you want to be sent off in this direction. There's sort of a haze around that direction, which causes these shoulders. So you'd like it to be a delta function here at the one wavelength of light that you sent in. This is a laser coming in at that one wavelength. So you get this haze around there, and then you get this additional part of sort of a diffuse scattering off the grating. So pretty much all grating spectrometers have this to greater or less extent, and you have to characterize it. The way Moby, which I'll describe in a couple days, I guess, works, which is a hyperspectral sensor, is we send a whole bunch of different laser lines into the system, measure what this stray light is, and then correct it in the data as we get it off. So there's papers on how to do stray light correction if you want to do that. And you should characterize your instrument if you're doing a hyperspectral instrument. Example of what it causes, with Moby, we have 2 radiometers, one that does the blue side, one that does the red side. And before we do a stray light correction, the blue side in this overlap region looks like this, and the red side looks like that. So there's a mismatch between them caused by this scattered light. When you do the stray light correction, it brings down and brings the 2 things in conjunction with each other. And the important thing there too, you can't read this, I can't read it here, the font didn't work out. This is your light field again that we're looking at. This is what a calibration lamp looks like. And so, and it's also a problem with the stray light, the out of band problem with filters, is if I'm calibrating with this really red rich source and I go out in the field where I'm measuring light that's more blue rich, I'm going to get completely the wrong answer because the stray light coming, say, at this wavelength from over here might be different in the lab than it will be in the field. So you have to be careful with these different things as you do your calibration. And when you buy a hyperspectral radiometer from the manufacturer, you want to ask them about the stray light characterization. And have they done it, and have you gotten the data for it? Okay. So those are the 3 classes of instruments based on spectral responses, broadband, multichannel, and hyperspectral. And now we'll look at what they're measuring. And we'll start with the simplest one in a way, is plane irradiance. And irradiance is simply the amount of light that gets through a certain area. So the perfect irradiance collector would be a hole that you collected, that you knew the area of the hole, and you collected all the photons that went through that hole. That would be the perfect irradiance collector. And so here's a picture of something like that. It's got a hole here that looks the opposite of a hole, but it's a hole here. Light coming down into that hole. You have some filter to describe or to segregate which part of the light field you want, what wavelengths. And then a detector to change the light photons into electronics that you can deal with. The problem with this is that filters here, typically interference filters, say, have an angular dependence. And so the way the light coming in at some angle will get through a different part of the spectrum, will get through the filter than coming that way. So this perfect detector isn't going to work very well with filters. Detectors have an angular dependence on their response. And so it won't deal equally with the light that comes in at different angles. And in general, when you put something in the water, you like to have some sort of a window to keep it from being flooded. And that window then has different reflection coefficients depending on what angle. So you'd like to build something like this, but it's not really possible to build something like that. But that would be the perfect IRradiance detector. So everybody see how plane IRradiance works, okay? If you define it in terms of the Radiance Distribution, it's that, but let's just think about it, the amount of light getting through a hole. Real IRradiance detectors. So here I brought one in, one of Emmanuel's. A real IRradiance detector has a diffuser on the front. And if you could see off the side, what it looks like on the side is this. It's got that diffuser, and then there's a gap like this, and then there's a rim around the outside, okay? And so it occults the detector or this diffuser from light coming in horizontally, because if I had a hole, I wouldn't expect any light horizontally to come into it. And as you come up an angle, what this extra edge does is it sort of increases the area of the surface, all right? So what it does is it makes it so that when you'd have light that came in at a large angle that would mostly reflect off, it gets this extra surface to get a chance to get into the diffuser. And then once in the diffuser, some of it comes back to the back. You have a filter, say, that's back from the diffuser, so it restricts the angular distribution of light going through the filter, so you keep your spectral response more constant, and then a detector behind that filter. So this is a hyperspectral instrument. Now, do I say it there? Yeah, bold letters, good. An air sensor, this one is designed for air, and it's the surface reference you're going to be using tomorrow. Yeah.
The height of that edge, before we jump into the next thing, is that computed just from knowing what the reflection properties of the surface of the filter or the diffuser are going to be?
Okay, so the way you design one of these at the current knowledge state we have of plastics is you build a whole bunch of them with different heights, different widths, and you go and measure the cosine response of them until you find the one that you like, okay? That works very well, it gives you the cosine response. It is, I was just gonna get to that, is these air sensors are not the same as the water sensors, not because they're not waterproof, but because the water interacts with the plastic differently than the air does. And so when you look at this one versus, I didn't want to take the instrument apart, but you look at a water one, it'll be a completely different shaped button and stuff. Satlantic's done a good job at the cosine response, one of the data that I've looked at. Okay, so that extra area on the side, and it's all depends on the plastic, multiple measurements, yeah.
What kind of percentage error would you characterize that plastic making as opposed to our hypothetical perfect instrument?
I'll show you that in a minute. Okay. So, but this is the idea of what a IRradiance sensor is. I wanted to just point out that when it's an art and a lot of experimental going back and forth to design what this should be for the different sensors, and it depends both on the plastic and it depends on what your collection optics are behind there, right? So I can't necessarily just buy this piece of plastic and this little part in the design unless I have the back matching too, the collection back here working the same way. It'll be different for mine. If you go,
I mean, the example of where we found the problem is we have radiometers on the clothes, and when we're doing measurement in the water, and then it comes out and goes in the air, and we're doing measurement in air, it turns out you cannot use the same radiometer. you have to completely characterize exactly how the cosine response changes for the same sensor and be able to deal with the uncertainties.
Yeah, and when tomorrow when we do the lab, you'll see this one will be set up in the air, and you can see the one that's in the water, and you can look at the difference in the design of the two. Now, just to point out for fun, this is Ocean Optics, builds these nice little spectrometers that are pretty handy to use, fiber optic coupled. They'll sell you a little Radiance detector that looks like this. It's a little plastic diffuser. I'll pass it around, reset from the surface. You can guess about what the cosine response, I've never measured this because it doesn't even worth the time, but you can imagine how good that cosine response is relative to what the design should be. You can check it out. Okay, so there's that. Here's the answer to that question. This is from Giuseppe Zabordi. Made these measurements for an air sensor, actually for, I think, a selection of Satlantic instruments. And so this is the error that you're getting due to the from the cosine, imperfect cosine response as a function of incident angle for the light. You can see that up to around 40 degrees or so, it's very tight. This is minus 10%, plus 10%. And really where you get the problem is at these large angles, 70, 80, 90%. Okay, so those start coming in. Let's see. Now,
Adds a lot of uncertainty if you're doing high latitude work in your solar beam, which has most of your energy. Is that what you're talking about?
yeah. So it'll give you an error that depends on the radiance distribution of whatever the light is you're coming in with. Just for an example here, I'm going to talk about these graphs probably later more. But this is the black line here is the downwelling radiance distribution. Here's a picture of it coming into my camera system. The little arrow here is where the solar beam is. What I really wanted you to see is that for the downwelling radiance distribution, it's centered, it has a nice peak and it falls off largely toward the edges. This is minus 90 degrees and that's plus 90 degrees zenith angle, so as you go down the horizon one way or the other. So in terms of this cosine response, an irradiance detector for the downwelling light field is going to do a pretty good job because it does a really good job where most of the light is, and where the errors are is where it's a smaller portion of the light field. And this ends up being compressed a lot in the surface because of the Snell's law refraction through the surface. We've already talked about that somewhere, I remember. So for downwelling light, an irradiance collector works pretty well, even with a little bit of error on the edges. This is the upwelling light. The y-axis here is 0 to 5 in all of them but this one, which is 0 to 3, and this one, which is 0 to 3. What I just want you to know is this is multiple different wavelengths. But the main point is in this side is low chlorophyll, this side is high chlorophyll. At low chlorophyll light field, the radiance distribution, it's still peaked a little bit on the edges. There's more light. If you look going down, looking straight down, there's more light off to the horizon than there is looking straight down. So this cosine response error will be a bigger problem for upwelling light than it will be for downwelling light. So the upwelling irradiance measurement is a problematic measurement. When you go to high chlorophyll, it's even more of a problem. There's a lot more light at the horizon than there is looking straight down. So irradiance detectors, collectors have a problem for upwelling light field. The other thing I should mention is there's something called an immersion factor for irradiance collectors. And I just drew the normal incidence here. I tried to put a lot more words on the slides than I normally would, okay? So anyway, this is just for I've just drawn the normal incidence. This is a detector light field coming in here. let's see. So you have the light coming in, the collector, and some sort of detector that's back behind that diffuser. That's probably in air because we like to keep our instruments in air for the most part. If I do this measurement in air, somewhere as the light comes in, it'll bounce around in this diffuser. Some of the light will bounce back out. Some of it will keep going through. If I now put that in the water, because the index refraction difference between the water and the plastic isn't as big as it is in air, more light will actually escape and once it's in the diffuser, will actually bounce back into the environment, which means there's less to get back into the detector. We do our calibrations most of the time in air. The lab works better that way. So we have our calibration in air. We put it in water, and the amount of light from the outside that gets into the inside, into the detector, changes. And so there's this immersion factor that you have to calculate or actually have to measure for your instrument. So the manufacturer, when you buy one, should give you an immersion factor to it. You can check it yourself. There's a paper I reference here, Hooker and Zabordi. There's a whole history of doing this immersion correction. So it's important to make sure you have the immersion correction in there. In terms of this class, so one, when you go out and buy one, you want to have the immersion factor and you want to check it off. In terms of this class, when you use the radiometers tomorrow and whatever, there's a little checkbox that you want to make sure that if you're using that detector in air, you've got the checkbox proper for not applying the immersion factor versus when you have it in water. Okay, and this is in the instructions for the lab, but it's important to use the immersion factor when you're supposed to use it and not other times. And this is it can be, I think it's like 30% or something. It's a large factor. Okay, and in terms of what irradiance numbers look like, here's downwelling irradiance. The units I like are microwatts per centimeter squared per nanometer. And so at the surface, this is just above the surface. Numbers are on the order of 100 or so in the visible range, a little bit above 100 microwatts per centimeter squared per nanometer. This is for the downwelling field. As we go to different depths, the bottom depth is 26 meters. This water looks like it's absorbing a lot in this blue, so it must be somewhat, it's blue water station, is what Marlon says. Okay, so this just shows you that we get rid of the irradiance in the red wavelengths because of absorption by water. And you're getting some phytoplankton absorption down here, and CDOM probably down here. Okay, so there it gives you sort of relative numbers to look at. And a green, for a green water station, that's shifted over to the green. Same thing. So this is just reference to see what numbers you should expect to give you order of magnitude. Okay, so the way you calibrate something like this is you get a lamp and you set it up. The lamp somehow has a calibration traceable to NIST, to the National Institute of Standards. For us, or I guess for the Europeans, would be the UK, I think, is who does the primary standards for the most part. Anyway, so you set the lamp you have has an irradiance at a certain distance, traceable to your standards of choice, and you set up the instrument at a certain distance from that. And if it's not at the calibrated distance that they give you, you can offset it by a 1 over r squared dependence. The light field will fall off as 1 over r squared from that lamp. There's all sorts of subtleties here for calibration that I'm not going to mention, but that's basically the general idea. Okay? It's pretty easy to calibrate it. Scalar irradiance. Scalar irradiance is important because we've talked about that in terms of phytoplankton. The phytoplankton doesn't care where the light comes from. So a scalar irradiance detector would like to collect light from all directions at the same time. The problem is that it's difficult to make something like that collects light irregardless of the angle. Let's see. So here's an example of what people used to use. If you saw, I don't have one here. It used to be biospherics, say, had a PAR sensor that was looked like a ping pong ball on top of a little rod. And so the ping pong ball would act like a collector in all the different directions. And the detector would look up into this diffusing ping pong ball and hopefully get a measurement that's representative of the scalar irradiance. The problem is there's always something underneath that ping pong ball that's going to be obstructing part of the light field. So there's other people have had ideas that you're going to take this and extend these a shield underneath to infinity or to a large angle, large distance, and this one would collect, say, the downwelling scalar irradiance, and then you'd have another one up here that would measure the upwelling scalar irradiance. The issue is both of them are measuring the sideways part, but in general, if you're measuring scalar irradiance, yeah. Good. Where?
Why do they do it with pole spheres instead of hemispheres? Why do they do it with like instead of with a hemisphere?
Well, you'd like, yeah, no. I came. Excuse me? What was that? No. People have done, so you have a hemisphere like this. What you like is to have the same projected area on each angle, so you come down to the edge and you're not getting that same area.
1970 or something by Niels Hyperspectral, where he looks at about 10 different ways you can build an instrument. Like you could do one like this, or you could have the little hemispherical bump, etc. And then in that paper, he shows you what radiometric quantity you're actually measuring with each of those designs. And I guess that's the one that sort of straightened people out, that you have to have this design to measure a downwelling scalar irradiance, and this thing that measures the hemisphere is like, I can't remember, it's half the difference of downwelling scalar plus downwelling plane or something like that.
Didn't
It's a nice little paper.
Daniel Spitzer, I think it was, and when Marcel was his technician, Marcel Vernard was his technician, he built this fancy sort of like this, except he blackened this, and he had one up and one down, and was trying to get Gerson's law out of it. But there was some using some combination of the radiometric factors. Anyway, this is the simple PAR sensor. And in general, if you're worried about phytoplankton and you've got a PAR sensor that looks like this and has a detector down, it's going to give you a pretty accurate measurement because most of the light's coming down, not as much as coming up, and it's not a big deal that it's being blocked at the bottom.
It's also important for photochemistry or photo bleaching of DON and things like this. This is the light field that you're interested in, not the ED or the ENOS.
Okay. Problem, I already did this problems. Okay. To give you an order of magnitude what the numbers look like, there's this term called average cosine, which is the ratio of the downwelling irradiance to the scalar irradiance. And since the scalar irradiance is measuring everything equally, the scalar irradiance is going to be a little bit higher, and this ratio for the downwelling light field is about in this example was about 0.7. For the upwelling, remember the edges are more important for the upwelling light field, And so the scalar irradiance, the ratio between the upwelling irradiance, which has a weighting of cosine, so it sort of tries to eliminate the horizon, divided by the scalar irradiance, that ratio is much less. Okay, so 0.7 or so. It's related to the incident sun angle and how much scattering you have, and I'm sure Kurt will talk more about it as he goes.
Note that the average cosine should be mu d equals ed divided by e naught d, right?
Mu d, right? Yeah.
Yeah.
So yeah, so the mu d ed over E0d, or mu would be E, the total irradiance, divided by
But it's
the
the net irradiance, right?
net irradiance, right?
Minus EU over mu numerator. So I think Kurt covers that later, but just make sure you put D's there.
Yeah.
That's correct.
I don't expect you to really remember this too much, except you could go back to this lecture if you wanted to and see a number. Okay, radiance now. Radiance is taking your radiance detector. The simplest thing for radiance is it's taking your radiance detector and limiting the field of view to within some solid angle. So it's the amount of irradiance this would measure divided by the solid angle of your acceptance. So the simplest one is this Gershon tube. We've seen this already once. And so basically that's what that is. So simplest is a Gershon tube. And most often we measure radiance with something like a Gershon tube. There might be a lens in there to define the angular distribution a little bit better. I didn't bring the radiance detector in. But typically what people do is measure the upwelling radiance at one angle, typically nadir, just coming straight up. All right. Now, to use the radiance in all those other equations that we had on Kurt's poster over there, you need the radiance in all the different directions, which means what's called the radiance distribution. It's the collection of the radiance information from all the different directions. You can either measure that in individual directions, and I'll show you a picture of Tyler's measurements or his instrument from the 60s, or you can do them all at once with a camera lens of some sort, which was sort of developed first by Ray Smith, and Tyler actually, and Petzold, I believe. Here's an example of a radiance distribution instrument. It had a little fin with a little propeller to do the angular direction, and it had these two tubes that would measure the radiance in both directions as it rotated around. This is the instrument that developed or measured the Pondere measurements that for a long time were like the gold standard for radiance distributions. Here's a picture in the courtyard of the Viz Lab in San Diego showing them testing this instrument. I don't know most of these guys except this guy. I can recognize his shoes. That's Jerry Edwards, who was an engineer at the Viz Lab for a long time and was there when it closed. The other guys, this is probably in the 60s, so I don't recognize most of them. You would think I'd see Dr. Duntley, but there's no one wearing a tie, so Duntley's not in the picture. Here's a picture of the instrument being deployed off that barge in Pondere, and so it's nice image. Anyway, nice picture. Excuse me? Okay, the Viz Lab had this experiment going for a while, so I'm sure the light bulb was at night. They would do other measurements where they had a very sensitive radiometer down in underwater, and they'd bring it up to the surface and check out what the light attenuation looked like from the light bulb. I was looking at that earlier going, that's the only thing it's got to be, is what that was. Here's a more modern radiance distribution instrument. This is new RADS. Here's what it looks like. It has a fisheye camera, so it measures the whole hemisphere at once. spectral filters inside of it, and a CCD array in the backside. So you get the whole radiance distribution in certain wavelengths. This is a picture of it floating away from the ship to measure the upwelling radiance distribution without ship shadow. Here's examples for nadir radiance to give you, once again, numbers. This is the sky irradiance, and here's the upwelling nadir radiance in microwatts per centimeter squared per nanometer per steradian is the green line. And so in this case, the blue water station, the downwelling light here is about 160 microwatts per centimeter squared per nanometer. And the upwelling light is on the order of 1.4, 1.5 microwatts per centimeter squared per nanometer per steradian. You see the blue water, the light's blue. The green water station, the upwelling light's centered here at 550, so it's green. And since you can't read the axis, I tried to write it all down at the bottom.
Is that from depth or is that above?
This is, okay, so these symbols here, ES0 plus, that's the downwelling sky irradiance right above the surface. And LS0 minus means it's the upwelling radiance just below the surface. Okay, it has not been transformed through the surface. Here's examples of the radiance distribution. I showed these already. One property you see here, this is at 1 meter, 5, 10, and 30 meters. As you go down in the water column, what you see is the little arrow represents, it takes a bit of time with this instrument to do a profile. So the sun angle changed while we were doing the profile, but you see that here the peaks are pretty close to exactly where the sun position is. As you go down in the water column, here's the sun position, the peak moves toward the center. Theoretically, the radiance distribution should end up being centered in the downwelling direction and at one point get this asymptotic shape that only depends on the light field or depends on the inherent properties of the water and no longer depends on the incident light. It's caused because larger angles end up getting scattered and absorbed over the longer path length it has to transmit through the water to get to some depth. So there's an example for the downwelling light field. Here's an example for the downwelling light field also, and you can see this effect a little bit more here at this 30-meter station, especially for the red wavelengths. That's 589 nanometers, 442, et cetera. I can't remember where that's from. Here is the same sort of thing for clear water for Hawaii. Notice that it stayed much more peaked, but you're getting that effect where it's moving toward the center, even at 50 meters. No, it's a gradual effect as you go down in the water column. If you, and it depends on the absorption and scattering in the water. I've seen this effect at 1 meter when I'm in South Bay in San Francisco, where the water is extremely turbid with a lot of dissolved organics and stuff. So it's a gradual effect. Yeah.
So just the benefit of using a radiance distribution is to see the effect, to see that angle effect.
The benefit of using the radiance distribution, I'll talk about in a minute for measuring the upwelling radiance distribution. The overall philosophy would be that the radiance distribution gives you all of the information. If you can measure the radiance distribution perfectly in a profile, you could derive the scalar radiance perfectly from it, the downwelling planar irradiance, you get everything from it. So that's sort of, and it's good for comparing to doing closure with radio transfer models. In general, it's more complicated than most people want to deal with. And calibrating these things is a long, time-consuming process. And that's why I would have brought in a radiance distribution camera system to this lab so you could have a chance to play with it. but there's only 1 or 2 of them in the world, so it doesn't seem like a very transferable thing to give you. Yeah. And in terms of the radiance distribution, to show you something else, which will be important in a minute toward the end, is that in clear water, the radiance distribution is more uniform, especially between these angles of 40 and 40 degrees in nadir angles, versus in turbid water or more high chlorophyll, more absorption, it's more cupped. The edges, it's much brighter toward the horizon than it is looking straight down. And that's going to be important for us in terms of remote sensing in a little bit. Okay, so the higher the chlorophyll, the more cupped I like to call it the radiance distribution. More variation with angle. The way you calibrate a radiometer, a radiance detector, is you either have a lamp, or you take your irradiance source from before, shine it onto a plaque, a spectral reflective surface that, so a reflective spectral reflective surface that you know the reflectance of, and you view that that plaque with your radiometer and hopefully have a uniform radiance source across there that you're viewing. Or there's these integrating spheres that you can get. So they illuminate the inside. They're all white coated on the inside of this, so it reflects multiple times. And you have your instrument viewing the inside to try to get a nice uniform source of radiance. Most of the time people are going to do, this is a lot easier to set up and keep calibrated than that device. Yes, sir?
What is the difference between both in terms of, what's the difference between both methods? I mean, I read a lot that like integrating sphere is better, but why?
Okay. If depends on who you are, okay? If you look at this, there's going to be a certain amount of, if you buy the lamp or you get the lamp somehow from NIST, we'll just do US for a bit. If you get the lamp from NIST, it has a certain amount of uncertainty associated with the irradiance that you get that value. You have a spectral on plaque, there's a certain amount of uncertainty with that. So that when you look at your absolute uncertainty of your calibration when you're done with it, you have to include the uncertainties to the lamp values, the uncertainty to the plaque values, so now you have sort of an expanded uncertainty, combined uncertainty. Best case, your integrating sphere, you've sent it off to NIST and they've done the calibration at their source, and now you only have one of the uncertainty contributions. So that's good there. Simplicity in most labs, it's more likely you're going to do this than have a integrating sphere that's calibrated real well and gone back to NIST. To do a calibration at NIST of your integrating sphere is probably like a $10,000 or $15,000 exercise. Versus you can buy a lamp that's at least been secondarily calibrated to NIST for a couple thousand, and the plaque is on that same order. The thing you want to make sure when you're doing this calibration is, I mean, there's 100 things to make sure of, but one thing is you want to make sure the plaque is big enough so the sensor is it fills the field of view of your radiance detector, and yet you got to be a little careful because the bigger the plaque, the irradiance from the lamp falling on it is going to vary over the field of view. So there's all these very subtleties going back and forth. If I can go over those with you if you like. In general, most people are going to go this way. Very few labs are set up to be able to do that. I have an integrating sphere in my lab that's a 1 meter integrating sphere, beautiful sphere. And I've never gotten to calibrate at NIST because it's just too much. I do the radiance calibrations this way. Okay. Radiance detectors also have immersion factors. You calibrate it in the lab, typically in air, so that if you have a window, the transmission from glass to air is different than from glass to water, so you have to account for that. The other thing is a lot of radiance detectors have a flat window. And so the solid angle acceptance changes